This is Adam and Michael, and we did our project on accuracy of different transient methods for a low Fourier number cooling problem. We took a piece of stock of polyoxymethylene about 2 inches in diameter and put it in the wind tunnel and tested at different velocities. But we designed our experiment to have a Fourier number below 0.2 because, as you can see in this graph here, the orange shaded region is very curved and has lost its linearity, and so it's a little bit harder to find using the equations. So we're finding which approximation would work best. Now there are some exact solutions, but they take a really long time to do, and we don't want to do that. So we're finding which one would work best. And so to design our experiment, we found how long we could have our specimen in the wind tunnel to have a Fourier number that's still below 0.2. So we designed it for about 0.18, and our time was about 600 seconds. So we did it 10 minutes for each velocity. And then we saw for the velocities, we did a free convection, so no velocity in the air or in the wind tunnel, and then a velocity of about 4.5 and 31.5. We tried to have specific BO numbers that would fit on the graph, but because of just complications of getting the velocity to be exactly right, and also for some reason the wind tunnel isn't going above 31.5 miles or meters per second, we didn't get the exact values that we were looking for, but they still worked for the scope of our experiment. So we did our experiment testing on the surface, the temperature on the surface, and we put it in a heat bath and then measured how much it cooled in that 10 minutes. And so our experimental results showed our theta, which is using that equation there on the left, is about 0.18 for free convection, 0.529 for forced convection, about 4.5 meters a second, and 0.33 for 31 meters per second. So we compared our results to multiple different equations and also graphs. So using one term, we compared it to the experimental data. Our percent error was pretty small at the beginning and then gradually grew. So one term turned out not to be the best for all of our problems. And same with lump capacitance. The BO number for free convection was actually pretty close to 0.1, and so that's why it was more accurate. However, as we got further down with higher velocities, it proved to become even more inaccurate, 100% inaccurate for 31 meters per second. And then we used the BO numbers that we found using lump capacitance and one term. And this graph here, we use the one term BO numbers with this graph and found approximated about what the different thetas would be. On the left side of this graph is theta, and on the bottom is the Fourier number. And in the middle, those different lines are 1 over BO number. And then comparing these graphs, we come with a percent error increasing from 0.7 to 88%. And then the lumped capacitance BO numbers gave us a little bit different and a little bit more accurate numbers actually. So using the same process as the one term graph before, we found our thetas. Theta is the axis on the left, Fourier number is the axis on the bottom. And it was actually quite a bit more accurate throughout. And we'll compare everything here in a little bit. So the semi-infinite, using this equation that we've got, is pretty ugly, but it turned out to be more accurate than lump capacitance or one term. And it was pretty cool to be able to figure out how to use this equation. This wasn't one that we really used in class. We had to find it in the book. And so plugging in this equation, or plugging our numbers into this equation, we found these percent errors of 9% error to 79%. And then we did multiple term solutions. And we used this equation and plugged it into a solver in Mathematica, and then graphed that solver, and then found at 600 seconds where it lies on that graph. And then we took that temperature and plugged it into the theta equation as seen on this slide, and we found our percent errors and everything else. Now comparing everything, free convection lump capacitance was the most accurate, and so that proves that the BO number below 0.1 lump capacitance works the best. And then for our BO numbers above 0.1, the ones that worked the best were the graph, where we use the lump capacitance BO number. So that's our results, and that's what we would recommend that you use when you're just trying to find a quick answer.